All right, the next type of problem I wanted to visit with you about is vehicles. So let's talk about vehicles now. And if you look at this set of vehicles, you can see that the normal forces definitely change as a result of acceleration. So here's a dragster, or a car at a drag strip anyway. He's clearly got enough traction here. He's got enough force here that the front end has become very light. In fact, the normal force at the front end is equal to 0. Same with that one. This one you may see that as well, but here we have a rear-wheel drive vehicle trying to accelerate in this direction. The force of friction is going this way, which has caused the front end to be just a little bit light. When the front end gets a little bit light, you can see that the normal force at the front end is different than it would be under a static, just as some of the forces in the y is equal to 0 and moment equation. In other words, a static condition is different than the dynamic condition. And that's what we're trying to evaluate in our vehicle type analysis. So vehicles then in translation have several conditions that we may need to investigate and evaluate. So again, in general, if it's translating only, there is no alpha, and we've already talked about that. So I alpha is equal to 0, and there's also no acceleration in the y most of the time. There may be some, there's generally not going to be any acceleration levitating off the road. However, there may be some conditions where we have an inclined plane and we may have some acceleration in the y direction and some, or in the x direction and some acceleration in the y direction. Most of the time, we'll be considering only direction like this, so that levitation or acceleration in the y is equal to 0. But a vehicle then would have several conditions that we would want to talk about, whether it's either braking or accelerating. And if it's accelerating, is it have front wheel drive only, or just rear wheel drive only, perhaps or perhaps all wheel drive? If it's braking, does it have only front brakes, or does it have only rear brakes, or perhaps it'll have all wheel brakes? And it may be slipping. And what I mean by slipping means if it's under acceleration, are the rear wheels spinning? If the rear wheels are spinning, that they've broken through the maximum force of friction barrier, and the force of friction is maximum, which means that it is mu normal. If it's not slipping, it may be just accelerating, but it hasn't slipped. They're not actually spinning, so it's just a force that we would need to evaluate. If we're braking, we may be slipping by if you were skidding. If you've clamped on the brakes and your front wheels are locked or the rear wheels are locked and you're skidding only, therefore then the maximum force of friction applies and force of friction is mu normal. Or they may not be slipping. In other words, it's just a force to evaluate. The next thing is flipping condition. Is it lifting up the front end? In other words, has the normal force at the front actually gone to 0 like in these pictures? Or is it just got a little bit lighter and that we may need to just figure out what the normal force is like in those pictures? So that would be flipping versus not flipping. And then the last case would be whether we have one CG to worry about or whether there's multiple CGs. All right, so generally what we're trying to find is either or both of the acceleration and the normal forces on one on either the front or the rear wheels. The sum of the forces in the x equation applies, and generally we'll have to find some moments about one or the other, either about the CG or using one of the other contact points as our point of doing our moment equation. All right, so this is a picture of a motorcycle. We went through this in class, so I'm not going to do this again. But you can see that the maximum acceleration, or many times that's what the question is, how fast can it really go? Well, the maximum acceleration is certainly limited by how much power the motorcycle has. But after that, it's limited by whether or not it either flips over backwards. And you can see that once it starts flipping, it's going to keep going. So that's going to be the maximum acceleration that would occur is whenever this normal force just barely goes to 0. The other condition that may happen is whether there's enough friction in the back. Even though you have enough power, you may start spinning the rear wheel. And if you start slipping, then you can't go any faster than that. So once you have enough power to either flip over backwards or friction or break friction, then that's what our limiting acceleration is all about. So with this forklift, we have a vehicle under translation with 2 centers of gravity I'd like us to visit about. So here's our question. We're traveling with a constant speed. It gives the constant speed as 9 feet per second. We want to find the shortest stopping distance without causing any of the wheels to leave the ground. Well, imagine what's happening here is you've got a load on the front end, and clearly it's going to be a little light on the back end anyway, but we're going to jump on the brakes and we're going in this way with the constant speed. And this will become the point of rotation, because if it loses contact, it's going to lose contact at A. So in the picture of our problem, we're going to put a deceleration. The force of friction will be acting at B, be going in that direction because our velocity is going in this direction, and A, the normal force at A, will be our limiting condition, and that's where we're looking at. So this is a flipping problem, a braking problem, and in this case it's a two center of gravity problem. And we have to figure out how this is going to affect the normal forces at A and B based on the fact that we have two centers of gravity. So the first thing we do is find out, or we draw our free body diagram and discover where all of our pieces are. All right. So in this case, I drew a free body diagram of just the lift truck and a separate free body diagram attached, of course, with the load. Each of these centers of gravity will have their own mass times acceleration vector. So I'm going to draw that with a double line here: mass times acceleration of G2 and a mass times acceleration of G1. The X and Y forces are going to be, well, there's an mg acting through that G, there's an mg acting through that G, there's obviously a normal force at A and a normal force at B, and then there will be a force of friction that acts through, or acts at the front wheels B. All right, let's define positive. I'm going to call in that direction positive, in that direction positive for Y. I'm going to call moment as positive in the counterclockwise direction. So let's look at our moment equation. Because I know that the because I know that A goes to 0, what we'll find with some experience is that some of the moments about B makes a lot of sense, because that way we don't have to, we've already got the answer for A, we don't have to resolve it again. So let's just say the sum of the moments about B is equal to the sum of our mass times acceleration vectors times our vertical lever arms, or times y, plus the mass times acceleration in the y direction, which would be up this way, times our x values, plus our IG alphas. All right, so again, we know that it's not rotating, so that term goes away. We know that it's not levitating or accelerating in the vertical direction, so that term goes away. So all I have is the forces times distance on the left side is equal to the results of those forces times distance. In other words, the mass times acceleration times the y on the right side. We have two CGs, so some of the moments about G is possible but more difficult, and I'll do that on the next page. And the point of rotation is B because A goes to 0. All we have to do now is just plug this thing into our equation, and we say that A times its distance, this is 5 feet, that goes to 0. I have 2,000, which would be this mg, times this lever arm, and that's going in the positive direction, the counterclockwise direction as I defined it, so that's 2,000 times 3.5. The 900, this is this mg, is going in the clockwise direction around about point G, and it's got a lever arm of 4.25 from our picture. So I'm going to say that's 900 times 4.25. Those are the only two forces that have moments about point B, because the only other force would be, well, the force of friction, but that acts through B, and the normal force at A, but that goes to 0. All right, so what does that equal to? That equals my mass times acceleration vector. So again, let's look at those. I have this one going in this direction, and here's my point of rotation B. It is pretending to have a a clockwise rotation, because here's my lever arm, it's going in this direction, so it'd be a clockwise rotation. So I call that a negative mass times acceleration times distance vector. So that'd be negative mass of 2,000 pounds divided by 32.2 times the acceleration times my lever arm of 2.0. Now this is my unknown. I don't know what that acceleration is. All right, and then I'm going to have another mass times acceleration vector. Again, this guy up here, it's going to have this lever arm. It's also going in the clockwise direction, which makes it negative. And so I got 900 divided by 32.2 times A times the lever arm of 3.25 from that picture. All right. Both of those are negative. Now the next thing to recognize is that because these masses are traveling together, they have the same acceleration, which is what the unknown that I want to solve for. So with one equation, I have only one unknown, and that's the acceleration, and I can solve for that as equal to ax is equal to negative 14.76 feet per second squared. Again, it turns out to be a negative number, which is what we'd expected. I know that if I'm going in this direction, I'm slowing down, so my acceleration is actually going to the left. I defined it as positive in the beginning, so I would expect it a negative number if I did all my math right, and indeed I did. All right, we can also do this with some of the moments about another point. And just for illustration, I want to sum the moments about the first center of gravity, G1, and just to make sure that we can do that. So same free body diagram applies, same distances apply. So I'm going to sum the moments about G1 right here as equal to mass times acceleration. My sum of mass times acceleration is times their y bar. Now here's just something to note. If I sum moments about this G, the mass times acceleration of this mass goes through that G. So the only thing I have on my right side of the equation is this vector times this lever arm. Just that piece of it right there, which is 1.25. You can see from the picture right up there. So let's sum the moments about G. B is a normal force, which I don't know. A is a normal force, which goes to 0 because the condition is that it's lifting up. So I have that force. I have this force of the mg, and that's all I have on the left side of the equation. Excuse me. Then I also have this friction force, the friction force which is unknown. So these three forces would have forces times lever arms on the left side of the equation. So I've put those right here. I don't know force of friction. I don't know B. Clearly I know the 900. That is my weight coming down and its lever arm. On the right side of the equation, what I've got is, because this mass times acceleration goes through my G, I just have this one times this lever arm, which is 900 divided by 32.2 times my AG times 1.25, which is the lever arm. Now, how many unknowns do I have in this equation? I have AG, force of friction, and B. So I got three unknowns with one moment equation. If when I summed the moments about B, I only had one equation and I had only one unknown. But in this case, I got three unknowns. So I'm not sure this is a superior method, but it's for clarification. I just wanted you to be able to make sure you do that. So what other equations apply? Well, I still have some of the forces in the x as mass times acceleration in the x. Only force I've got in the x direction is that force of friction. So I'll say negative, because it's going negative to my positive direction. Positive directions. Oh man, I got that mixed up. Okay, let's change those. That's y and that's x. Okay, so some of the forces in the x direction is mass times acceleration in the x. Negative force. My sum of my masses, I got two masses and I'm looking for x. All right, then I need to do some of the forces in the y direction, and I got A and B have to be equal to those two CGs, and I can find out that B is equal to, well, actually I know because A goes to 0, I can solve for B directly like that. And that solves for one of the equations, and then I just have, or one of the unknowns, and then I still have the force of friction and acceleration, and that's two equations, two unknowns. Doing a little substitution here, and you can do the arithmetic, or prove my arithmetic if you want to take a screenshot. You can see that the acceleration is still negative 14.76. All right, so two distinct ways of summing moments about different points, and both of them work, obviously getting the same answer, which is good. All right, the last piece I wanted to visit with you about is things like this angle thing, and I've got a problem here I want you to visit with, I want you to look at, and here's a weight, a pipe being towed by this truck. It's got a little cable here, and the question is, if I give it some acceleration, in other words, the truck is being pulled this way, it's got some acceleration which is given. What we're looking for is what angle does this pipe end up rotating. It gives as under this acceleration, the angle that the rope has tied to the truck is a 45-degree angle, and we're looking for the angle of rotation of the wheel or the pipe. All right, so we draw a free body diagram, and we say that there's a tension in this cable. It's going up in that direction. There's going to be a cosine component and a sine component. We have an mg coming down through the center. There's going to be a normal force of C, and because it's being dragged in this direction, there's going to be a force of friction times mu c. All right, so the three equations we work with are sum of the forces in the x is mass times acceleration in the x. So what have I got? Got a t times cosine in the positive direction minus mu c going in that direction, and that's going to be equal to mass times acceleration of g in the x direction. Some of the forces in the y. We don't want it levitating or moving in the y direction or accelerating in the y direction. Therefore, some of the forces have to be equal to 0. So what have I got in the y direction? I got a positive c, positive t sine component, and a negative mg, and those have to be equal to 0. The moment equation, pick one moment that we want to try to evaluate. So I picked point A right here to try to do a moment equation. And what I'm going to say is that all the forces times their distances are on the left side of the moment equation. The results of those are on the right side. So here is our moment equation. Sum of the moments about A is equal to mass times acceleration of g in the x direction times this y bar. Here again is my mass times acceleration vector. I'm doing moments about point A, which means that I have this piece right here of a lever arm in this direction, in the clockwise direction. In the counterclockwise direction. So if I call counterclockwise as my positive direction, I've got mg times this distance right here, which is 0.4 cosine theta, or that's my theta, minus, in the trying to rotate in this direction, I got c times that same distance. So that'd be c times 0.4 cosine theta. Minus mu c. Now mu c is going in this direction, and it's got this lever arm. It's got that r plus this little r sine theta. So those are on that side of the equation, or that's that lever arm. And now that's going to be equal to what happens on this side of the equation, which is my mass times acceleration vector, and it's got this lever arm, which is the 0.4 sine theta lever arm, which is there. Again, it's going in the positive direction. If I do that, then I recognize I have three equations, three unknowns. My unknowns in these three equations are the tension, the normal force at C, and theta, and I can use some substitution magic and try to resolve for those tensions, or resolve for those three. We can also sum moments about another point, and I tried for, just to make sure I can do this, sum of the moments about G is equal to Ig alpha. So let's look at that. Sum of the moments about G, C goes through G, the mass times acceleration vector goes through G. However, now we have to take into account this cosine component times this lever arm, the sine component times this lever arm, and the mu c component times this lever arm. And doing all those, you can see that I've done this here, and you can again look at my math and make sure, but I still get a three equations, three unknowns situation. I still have my sum of the forces equations, mass times acceleration equations, and then my moment equation. Still have three equations, three unknowns. Not sure which is easier. I didn't resolve for the actual numbers here, and you can do that. Just want to make sure that you know how to set these things up. All right, well, I hope that helps you in your studies.